Hi, and welcome to this week's maths class. I'm Mike Seymour. Well, this week we're looking at magic numbers. Magic numbers as in numbers that in maths are really significant and do really cool things. Now, there are three of them that we're going to really look at today. One is pi, which most of you would know. The other is phi, which some of you will know. And the third one isn't really so much a number as it is chaos. It's noise, or as we'll be looking at it, turbulence. Now, you might be wondering why I'm standing here holding a rabbit. Well, one of the magic numbers that we're dealing with today falls into a whole equation which is to do with a thing called the golden ratio. Now, the golden ratio is related to a thing called Fibonacci sequences. And a Fibonacci sequence is a series of numbers that were derived by this guy, Fibonacci, hundreds of years ago because he was obsessed with rabbits. Yes, I got there eventually. He was wondering that if you had a rabbit, actually a pair of rabbits, and they were to, for example, have, well, basically mate, and they mated every month. And every month they produced another pair of rabbits. Let's assume also that they never died and they kept on going. So every month, like clockwork, they had rabbits. Because anyone that's ever had a rabbit knows that they tend to breed pretty much, well, like rabbits. And then after a month or so, the next pair of rabbits would somehow get pregnant, and then they would have a litter by the time we came around to month 2. So you'd start out with one pair, and then you'd have basically two pairs, being the parents and their children. Come the third month, you'd move to having the parents having another set of kids. So there's the parents plus two sets of kids. And so we've gone up to 3. And then what happens after that is that they have kids and the parents have another set, so another 2 are added, and we go from 3 to 5. And so we build out a Fibonacci sequence that moves along as in 1, 1, 2, 3, 5, 8, and so it goes up. And it keeps on going for basically forever. Now, why is this significant? Well, we'll see later in the term, but thankfully Fibonacci was completely obsessed with the mating of rabbits, and consequently we got an incredibly interesting, in fact probably the most interesting sequence of numbers in maths. But before we get to that, let's go back and have a look at pi. So we're going to look at a bunch of magic numbers. Magic numbers are, well, I don't know how to describe them really. They're just these bizarre numbers in maths that just happen to be. And it's really helpful if you understand them. There's pi, there's phi, there's a whole lot of things. There's actually noise that you need to understand. And I'll be discussing those three big areas this week. So let's start with pi and circles and I guess another magic number, which is why is there 360 degrees in a piece of geometry? Like, why do we divide up a circle into 360 degrees? And there's really obviously no particularly obvious reason for it, except for the fact that 360 degrees is probably based on the approximate number of days in a year. In ancient Babylonian times, astronomers were noticing that the stars in the sky, which kind of circled a celestial pole, seemed to do it in a year, advancing about a 3/60th each day, and they just decided to have that as their kind of mean. In fact, ancient calendars tended to run in Persian days into 360 days to a year. Another motivation actually from us is that 360 is actually a really great number because it's divisible by 24 things, including 1 and 360. So every number apart from 7 will divide into 360, which is jolly useful. And that means that we can do tons and tons of cool maths. In fact, if you wanted to get every number between 1 and 10, including 7, to divide into 360, 360 would no longer be 360, it'd be 2,520, but I'm just geeking out now. So it's a really useful thing. Having said that, while the divisors of 360 are 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, 20, 24, 30, 36, 40, 45, 60, 72, 90, 120, 180, and 360. That's terrific and really useful and great. It isn't, however, enough to do everything we want to do in geometry. So we have to then take our 1 degree and produce smaller increments because we want to have smaller than a degree. And so then we go into minutes. So you'll have 60 minutes in a degree, and of that you'll then have 60 seconds in a minute. Which of course comes from time. And that lets us now divide down our 360 into much, much finer details. And yet still, it's not the ultimate thing we want to do for maths. And so in most maths, we don't actually do typical angles in degrees. What we do is we do angles in radians. Now a circle has 2 pi radians. just to be clear about that, we define radians to be the fact that there are 2 pi radians in a circle. It's the thing that gives it its definition. And this is like a much more sort of useful thing normally to work in terms of computers. So inside a computer, it's probably measuring your angles in radians. So the thing you have to remember is that if you had 2 pi radians equaling 360, then if you divide that down, you'll simply get that 1 degree is pi divided by 180. Now, we do use radians quite a bit in maths when programming, but as this is not a programming course, I'm not really going to go into it in great detail. But it is useful in many trig functions and simpler things. It has kind of natural properties in terms of maths that tend to work and outweigh the convenience of dealing with things just in degrees that we're used to from being a child. There's nothing wrong with radians. You shouldn't be scared by them. They're just a different unit. Which brings us to pi. What is pi? Well, there's an old joke that a mathematician would express what pi is as being basically a relationship between the circumference of a circle and its radius. And that's totally true. Of course, a physicist would say pi is 3.1415927 plus or minus 0.000005. And most engineers would just say it's about 3. So there are a bunch of concepts that we need for you to know, and pi is one of those magic numbers that we need you to know. So you need to know what a diameter is, what a radius is, but also there's a couple of other concepts that are quite important. A locus is an important concept. So here I'm drawing a line, and if I do a locus, I just basically want to have another line that's equally distant from it. So a point gives you a circle as a locus. Obviously, any point on the circle is equally distant from the dot in the middle. But if you do a line, you get this kind of pill-looking shape. And then there are other concepts like tangents that we've come across already. And tangents lead, of course, to normals, and these are all important concepts. Now, pi is a number you just kind of need to know about, but it's probably the case that you do already, right? Because most people know about pi from school, and it's a very popular culture kind of thing. It appears in movies and stuff. It's an irrational number. It's a vastly long decimal number when you try and write it out as a decimal number. It just goes on tons and tons of digits in a very long line, and it's not a repeating pattern. It just keeps going. And it has tons of cool properties to do with circles that we love, like the fact that the circumference of any particular circle would be equal to 2 times the radius. And if you think about it as a diameter is half, radius is half of a diameter, you could have actually said this as it's equal to diameter times pi. And that's this thing about pi, it's just so fundamental to areas and surfaces. Like the area of a circle is pi r squared. But we tend to work in 3D. So we want to know, what's the surface of a sphere, for example, which would be 4 pi r squared, or the volume of a sphere, which would be 4 pi r cubed divided by 3. Now, r cubed is because if you think about it in 3 dimensions, whereas in 1 dimension, or sort of a flat circle, you've got like 1 radius. Obviously, there's a circle, there's 1 radius. And you go to 3 dimensions, you obviously have a radius that gives you that, but you also have a radius that goes this way, and you also, in a sense, have a radius that goes that way. And so, radius around x, around y, and around z, so it becomes r cubed, which is important because we also want to know what an ellipsoid is.
The ellipsoid works in exactly the same way. Imagine we have an ellipsoid here that's a solid kind of thing. It's going to have 3 degrees of rotation again, but they're just going to have different rotational aspects. But we can call them R1, R2, and R3, and they'll work in exactly the same way as we saw before. It just multiplies out so that, say, for example, the volume is equal to 4 pi R1, R2, R3 divided by 3. So basically works the same way. Of course, the radiuses aren't now the same. Okay, just in case you're wondering about a donut, so imagine we had a giant torus or a donut here. That makes sense. Okay, center there. Let's call that radius 1. Let's call that radius 2. So if we wanted to try and work out what was going on with the surface area of that, the area of that would be equal to pi squared, and then we're going to take R2 plus R1, and we're going to multiply that by R2 minus R1. So that's going to give us the area. What if we want to get the volume of it? Well, the volume of it is going to be pi. I've got to say, the only people that ever work these people out are people doing computer graphics papers, because I've never actually used a torus in a real job. Squared divided by 4. And so that's the volume and surface area of a torus.
Now, at this point, I want to just quickly explain something, because as I did last week, I just gave you some formulas, especially for the one for a torus, and I haven't explained in great detail how I worked out that the volume of a torus is what it is, or the area of a torus is this particular formula. And the reason I'm not doing that is because this is a 100 level course. And so a couple of people have asked, why don't I just go into explaining all of these formulas? I've just seemed to do a few, and then a couple of the other ones I go on and kind of just give them to you. And I'd love to do that, but it would mean that this wouldn't be a 100 level course. It would be either a 200 or 300 level course, and we'd spend all of our time just on vectors, or all of our time just on trigonometry or geometry, because these are huge areas of maths. What we're trying to do in this 100 level course is flag the maths you need to know. So in this case, you need to know pi. You need to know some of these formulas for working out things like pi r squared and also volumes of spheres and stuff. But I don't think at the 100 level course I need to give you it in terms of every individual formula worked through, nor would we have enough time in the course to do it. So pi is cool, and there's International Pi Day, which is the 14th of March. Email me when you get that one. And then even if you flip 3.14, you get pi, and there's worse maths jokes than that. There's the official second pizza theorem, which is the volume of a cylinder, which of course a pizza is a very flat cylinder, is the surface area times the height, right? So mathematicians, when geeking out watching Big Bang Theory, ask, what's the formula for a pizza? And it's actually, of course, going to be, if the radius is actually called z and the height is called a, it actually becomes pi zza. Okay, it's a bad joke. The point is that it's just everywhere in popular culture. In fact, there are even biblical references to pi. There's an example in 1 Kings 7:23, which says that basically pi is about 3. And if you actually read the piece, depending which version of the Bible you're in, it discusses that he made a molten sea of 10 cubits from brim to brim, round in compass, and 5 cubits in height, and therefore a line of 30 cubits did compass around about it. Which basically means that you've got 30 cubits, which is the circumference, okay? And a cubit, and this is important, is an arm's length, yeah? Anyway, so a cubit, 30 around, and so we know that the outside is equal to 2 pi r. So in this case, we can say, okay, well that means that it's equal to effectively, half of that diameter of 10, which is 5, and so we can do the maths, and we actually get down to the answer that it's 15 by 5 by their version of pi, which of course means that pi is equal to 3. Now, this is not to say that the Bible is mathematically incorrect. It's simply to say that if you're trying to measure maths using the length of your arm, it's quite possible that, like an engineer, you'd give an approximation of pi to 3. But the point is, whether you're doing it in practical terms, like you're trying to do qubits of molten stuff, or you're doing real-world stuff with a calculator, you need to use pi to do fundamental maths. But I'm not now going to give you what I've done in the past, which is the classic computer graphics example of that, because quite frankly, at the level we're at with pi, it's so fundamental to the maths that I kind of struggle to find a more advanced version that doesn't run us into a ton of other maths. But that's fine. I think you guys can probably agree that it is absolutely standard to all maths involving circles, volumes and diameters. And there isn't really much more to say other than that it is one of these, it's the prince of magic numbers. Now, let's get more practical for a second and go to a slightly less well-known magic number. But this is practical in the sense that if we're, which I think we are, doing a lot of creative work, design work, a magic number that's the real darling of the design and sort of matte painting set is phi, which is to say it relates to the golden ratio. So Leonardo of Pisa, or Fibonacci as he's known, in 1202, came up with the Fibonacci numbers, those rabbits that I was talking about at the beginning of the class. You remember? 1 month was 1 pair of rabbits, 2 months was 2 rabbits, 3 months was, and so it goes. And you get up a Fibonacci sequence, 1, 1, 2, 3, 5, etc., depending on how pregnant your rabbits are. And that's great. And I love that Fibonacci was obsessed with the sex life of rabbits. But the Fibonacci sequence becomes really, really significant, because if we take all of the numbers in a Fibonacci sequence and start actually working them out as a ratio to each other, and here we need to go higher in the numbers. So I've gone up to like 8, 13, 21, I think. but we need to go 34, 55, 89, 144, 233, just got me forgetting these wrong, 377 and 610. Okay, so once we get higher in the numbers, like 377, 610, the ratio between the two numbers starts to become this consonant. In fact, it's sort of like it deviates around getting towards this consonant, but obviously in the lower numbers, you know, the difference between 2 and 3 is not as well defined. And this constant, this number that we head to, is another magic number. It's a really key number. Let me show you how it works, though, if we were to build that out. Let's take those numbers that I was talking about with the rabbits, use them as areas, and to just build them out in terms of blocks or squares.
Okay, so the number sequence is, we draw this out, it's 0, 1, 1, 2, 3, 5, 8, etc. Now I'm just going to interpret those numbers slightly differently. I'm going to do something that's of 1, and then I'm going to do something of 1. So I basically got 2 1s here. I want to now have something that's a 2 by 2. Well, I'm going to draw a separate thing that's 2 by 2, and I'll do this properly again, but quicker with animation, but just that's obviously going to be a 2 by 2 because we can see that. That's sort of graphically about the same. And now I want to do a 3 by 3 because that's the next number in the sequence. Well, if that's 2 units high and that's 1 unit high, that's obviously a 3 high. So to draw a box that's 3 units by 3 units, I can do that there. Okay, so now I've got a 3 unit. Well, the next one I need is a 5. And if you're looking carefully, you'll see that's 1, 2, 3, 4, 5. Okay, well, I can do a 5 by 5 down here. So that's pretty easy. So, imagine that's a 5 by 5 box. And so it goes. You say, well, I need an 8. Well, that's like 5 units up here, plus another 3 gives me 8, and voila, I now get an 8. And so if that's like an 8 by 8, and that's a 5 by 5, and that's a 3 by 3, and that's a 2 by 2, and then obviously a 1 by 1, you can see how this is working. It basically builds out. Now, what I'll do more elegantly in a second is do that quicker, but the trick to consider is that area interpretation of these numbers just keeps going, but it actually gives you a lovely spiral if you kind of do that. And that is the basis of a nautilus shell, and in fact that is the most purest form of a spiral that we have. And you'll see this drawn quite quickly, and I wanted to do one by hand to try and explain it, because I often find that when these draw out, these are kind of too quick to see what's going on. Okay, so let's explain how I draw it another way. So we know that the golden ratio looks something like this. Well, let's not start there. Let's start with something that is in fact a 2 by 2. Okay, so again, I'll do this again. It's fast, proper, sexy animation, but I just want to do it slowly so that you guys can see what's going on. That is a 2 by 2. It's a square. There is no special Fibonacci ratios or anything else going on with that. It's just a simple 2 by 2 square. Okay, so what I want to do now is I want to take a line, and I want to imagine that there is a point here that I'm going to draw up a radius line to here. Now imagine that is, I don't know, a plank of wood, and it's stuck on the ground here, and it falls over. And so it kind of falls down, right? And you can imagine it falling down. And it's going to land on the ground here. And when it does land, I'm going to say, oh, okay, well, imagine that I drew the box that came to here. Okay, so that ratio there to that ratio there, that is 2, and this is 2 plus whatever this bit is here, right? Or another way of thinking of it is to say that this is actually, this side here is actually 1 plus the bit that fell over, right? So clearly this fell over, so that length there should be, in my drawing, the same length as that. So let's forget about this 2 for a second. I know that this is 1, and I need to find out how long that plank is that fell over. And then I'd have the ratio between the 2 and the whatever this is. Well, how do I work out what that length is there? Well, hang on a second, that's 1, and I just said that's 2. So from week 1 we know that 1 squared plus 2 squared is going to equal that plank that fell over. So that's 1 plus 4, which is going to equal 5. Okay, 5, but I need the square root of that for Pythagoras, so it's the square root of that is going to be that number. So that's equal to the square root of 5. So in fact, my ratio is going to be the 1 bit here plus the plank that fell over, which is actually root 5, to 2. And so that is the modern day Fibonacci golden ratio magic number. That is the ratio that we've been seeking. Now, it just so happens that there are a million other things that you can do with this square, but let's just leave it at that for a second.
Okay, so 377 divided by 610 is going to be a long number like 0.61, I don't know, 803278688524 something like that. Okay, Fibonacci sequences. They give us our second magic number. Now, it isn't so much that we are obsessed with the Fibonacci number itself, though it is another great irrational number. It's just that it has this quality in geometry of being related to the golden rectangle. And the golden rectangle is much, much older than the Fibonacci sequence. It goes back to 300 BC. In fact, probably earlier. But we know way back, way before even Fibonacci, in different cultures, the golden ratio has appeared from the pyramids right through to even the first algebra book, which I think was in Iraq, in Baghdad, around 1111, around the end of the first millennium. There is an entire reference to this golden ratio, but it's actually expressed differently than we express it today. Back then they were calling it root of 125 minus 5 over 15 square root of 125. And I'll show you in a second, that's actually the same ratio number, because the maths of doing this is quite useful as we deal with when we talk about 1.6803398887, whatever it is. It is exactly the same number. It's this lovely ratio, but it's also this geometric property. Now, if it was just a ratio, well, okay, that would be kind of fun, and there's lots of cool maths we can do with it. But when you start seeing it in art, you start to appreciate why I say it's the darling of the matte painting set. So from Salvador Dali and the Sacrament of the Last Supper to the Mona Lisa, well, that's if you believe the Da Vinci Code types. But certainly in the Mona Lisa it does appear. Not that Leonardo actually sort of supported this in any way, shape or form. But then like iPod design even, pentagrams, nautilus shells, there are so many ways, as I said, from the Egyptian pyramids to literally pineapples and the way that seeds and flowers grow, that is defined by the golden ratio. So the golden ratio that we tend to use in modern day maths isn't the Babylonian one I said a moment ago. It's a simpler version, which is 1 plus the square root of 5 over 2. And why don't I show you now how that actually is the same as the one that the Babylonian guys had in their algebra textbooks, because apart from anything else, the actual maths of doing this I think is instructive.
Okay, so in our culture we just worked out 1 plus the square root of 5 over 2 is our golden ratio. We love that. It's terrific. Well, if we were in Baghdad in Iraq hundreds of years ago, we'd have come up with a completely different formula for our golden ratio. It would look like this: 125, square root of 125, minus 5 over 15 minus the square root of 125. That is literally the number that they came up with for the golden ratio. Completely different culture, different way of approaching things, pretty complicated number. But I'm going to show you, in fact, these are the same. And this is also really useful because it's a really good piece of maths and something that you should know how to do. We want to basically solve this being an ugly thing with square root at the bottom, and we can do that by doing a very simple trick. We simply multiply it by 1. Now clearly if I multiplied this number by 1, I'm going to get the same number, agreed? So let's say I multiplied that by 1, I'm going to get 125, square root of 125, minus 5, nothing's changed, over 15 minus the square root of 125. Now don't get freaked out by all the 125s flying around. That's all that's happened. Nothing's changed, right? Except what I'm going to do is I'm going to multiply it by 1 again, only this time I'm going to express the 1 as 1 over 1, because we know that 1 over 1 equals 1. Agreed? Okay, so this time I'm going to multiply it by 1 again, but I'm just going to pick a couple of different things to be top and bottom, but assuming that they're the same thing, top and bottom, right? It's still going to be 1. 4 on 4 is 1. 8 over 8 is 1. Okay, so I'm going to choose 15, and this is where it gets clever, plus the square root of 125. Just get a slightly smaller pen here. Okay, and the square root of 125 is going to have to be also the same thing, right? So these two numbers are the same, so clearly top and bottom are the same, it's still 1. And I'm just going to multiply those together. Now, it doesn't matter what order I've written them in, it just means this is 1, it's the same as this all equals the same thing. So let's do the maths. What I'm going to do is start by doing the maths down the bottom. So I'm going to have 15 by 15, which is going to give me 15 squared. Agreed? So that numbers multiplied together. Now, 15 has to be times this, so that's got to be plus 15 square root of 125. Okay, fair enough. Now I need to subtract these two, because that'll be minus 15 square roots 125. They're going to cancel out, and then minus these, so that'll be minus the square root of 125 by itself, or squared. Okay, now before we just go any further, let's just clean that up, because we'll stop us from freaking out. These bits are coming away from each other. If I take a square root and square it, it becomes 125. So I'm going to end up with exactly the same thing at the bottom. I'm going to end up with 15 squared, which we know to be, 225. Okay, minus 125, because it's a square root squared, so that becomes 125. Okay, so continuing on, because this seems too good to be true, that's going to be 100. Okay, see what I've done? I've multiplied the bottom by this number, and then I've just simplified it out. These bits cancelled, simple maths. Okay, so that is 100 at the bottom. Okay, and what's going to happen at the top? Slightly more complicated, but we can do it. We need 125 by 125, so that's basically a square of a square root, so we're going to get 125 again. So 125. Okay, now we're going to have plus 15 square roots of 125 minus 5 square roots of 125, okay, minus 5 by 15. So 5 by 15, because I'm multiplying 5 by 15. Okay, makes sense? Okay, so can I simplify that down? Well, you bet I can, because I know that that's 75, and I'm taking it away from 125. So that's going to leave me with the number 50. All right, so far so good. And I'm going to have, let's see, 10 of those square roots of 125 left. That makes sense? So I just subtracted those out. So that's it. So I could keep going, but I just want to point out one really important thing over here. If I have a number like 125, I can actually write that as being the same as, say, the square root of 5 times the square root of 25. They are the same thing. And, that's something we do in maths all the time. Okay, but the square root of 25 is 5, right? So that's going to be the square root of 5 by 5. Or, just written around the other way, 5 square root 5. It's just simple maths. All I've done is just simplify that down a bit. Now, if I do that over here, I'm going to end up with 50, the number 50, plus 10 times this little clever thing I did here, which was 5 and square root 5. Okay, that's good. I want a square root 5 because I'm heading here, don't forget. So, expanding that out, I'm going to get 50 plus 50 square root 5 over 100. Now, what I need to do is I need to just write this slightly differently, and the way we do that is we bring the 50 outside of brackets and say it's 50 times 1 plus square root of 5 over 100. Because clearly, if I multiplied it in, that would be 50 and 50 square roots of 5. Okay, now when I do that, it's pretty easy to see that I can cancel these suckers out, and I'm going to get a 2 there, and voila, the formula that I'm left with, this formula, is going to be 1 plus the square root of 5 over 2, which is the same formula. So even though these formulas were bridged by completely different cultures, they're actually expressing the same appreciation of the same golden ratio in completely different maths.
Okay, so it's not even just man-made stuff that has this golden ratio in it. In fact, we can extend out to this to so many aspects of nature. Now, this will become even more important later in the term, but the classic that's always used is sunflowers. If you look at this picture of a sunflower and you look at the seeds, you can kind of imagine that there's a spiral coming out around from the center of the flower. And there's another one going the other way, of course, which defines that sort of classic shape of the sunflower seeds. Now, what's really interesting about this is if you count on any particular sunflower how many spirals go out, and then count the other way how many spirals go the other way, you're going to get two numbers like, well, typically something like, say, 34 and 55, which just happen to be next to each other in the Fibonacci sequence. And this is like freaking me out when I first saw this, because literally you can pick different types of flowers, different types of things, and you will find that the way that the seeds are packed is the most efficient way that nature can do it. And they happen to be nearly always with matching Fibonacci sequences. In fact, so here's a different one. This is a daisy, right? Daisy has exactly the same property. It packs the seeds the way nature knows best, and the daisy exhibits exactly the same phenomenon. And it just keeps on going. And it's actually fair to say that this is sort of programmed into your DNA. It doesn't matter what culture you're from, because as I've tried to indicate, over time, over Babylonian or Indian or Western cultures, we tend to, whether it be an Egyptian designing the height of a pyramid or Ives designing an iPod, we just find these ratios naturally appealing, and so they get put into stuff. Now, I'm not saying that everything should be this way. Obviously, if you have some really good design decisions for some other reason that require a completely different aspect ratio, there's no reason not to do it. But it's pretty interesting that when you are designing stuff, that throughout history and throughout multiple diverse cultures, this is what we naturally come down to. So, pineapples. How the hell did I get to pineapples? Well, literally, pineapples do the same thing with the seeds, only instead of going out like fanning left and fanning right, we actually count around them. So if you were to take a pineapple and literally count how many, lines of sort of spirals there are on the outside of a pineapple going to the right, and then stop that and go the other way and count it to the left, you'll, of course, find two Fibonacci numbers that are actually next to each other in the counting order. And that's just the way it is. It's just everywhere in maths, it's everywhere in nature, and it tends to turn up everywhere in actual design, architecture, painting, tons of stuff. So that's fine, that's totally cool. But what I want to do now is get back to some more hardcore maths, because as terrific as it is and as predisposed as your brain is to think that's lovely, I want to go back to pi for a second. Now remember when I said that pi ran out to tons and tons of digits. There are people that have calculated that to vast, like millions of decimal places. Anyway, imagine for a second that we were talking about pi, and I said to you, I'd like you to write down a section of possible numbers from the sequence of pi. There's a lot of them, right? So you say you come back and you say, okay, sure. And you want them to be believable, right? Like you're writing it for a script or something, and I'm some scientist, and I'm like going to run out these numbers in dialogue, yeah? And so you would come back, if you're a normal person and haven't already seen this class, with something like, 51870721134. Nice dozen random numbers, right? They seem like random numbers, at least they seem like random numbers to most people. And what if I said the answer to the same question when you asked me to write down, in my script, a dozen or so random numbers that I wrote down, 99999999837. You'd say, well, Mike, there's a problem on the page 3 with the script because you're trying to write down a bunch of numbers from pi, and you've not written down a random number. You've written down like a ton of 6 or 7 nines and then 837, and no offense or anything, but no one's going to believe that that's actually real. And the problem is that's exactly not true. Because the first one is actually the last dozen or so numbers up to the 762nd digits of pi, and the numbers that I read out, the ones starting with 9, are actually the next 12 or so numbers that follow after that, right? Literally the next numbers in the sequence, because I looked them up, I'm that much of a geek, is actually 999999837. And so the reason I'm telling you this is because what I want to move to now is the problem of randomness, and how we're programmed to see patterns, and we give like meaning to patterns. And the reason I want you to understand this is because while pi and the golden ratio are incredibly useful, and you need pi in particular to work out things, and golden ratio is particularly relevant when we're doing matte paintings and design and artwork. Actually, these are not the things that you're probably going to use the most when it comes to magic numbers. The thing that you're going to use most as a magic number isn't in of itself a number, it's a concept, and that's the concept of noise. There are a gazillion places in computer graphics and in visual effects, compositing, even in camera design, sensor design, where you need to know about noise. And you need to know about noise and turbulence and the difference between the two. And it's this that I want to finish up the class with, because while I think we've had some really interesting concepts so far and a little bit of cool maths, it's this that's the area of mathematics that I find to be the most important kind of magic number. Many other people wouldn't lump this in with pi and phi. They would just say they're completely different concepts. But I think they are. I think they're exactly the same concept. It's something that you need to understand to be able to manipulate, to do stuff, and it will appear much more frequently in a user interface of a program. It is much more likely that when you're doing a particle system or a design or texturing or anything else, even if you're dealing with a red camera, worried about how an Arri Alexa does its, signal to noise ratio, everything's going to much more common. You're going to hit across the concept of noise and turbulence. And a really important part of that is that noise, while existing like white noise, it is in fact not nearly as natural as turbulence. And it's turbulence that we're going to need to understand.
So let's imagine this is our field, and I'm going to just draw a really simple picture. And it's top view looking down on our field. And I say I want you to put in a bunch of trees, and I want the trees to be randomly spread out over the field. And so this is what, very bad trees of course, but this is what tends to get drawn by most people. Yeah. And obviously, if you're clever, you won't draw this, but this is what many people would draw if they were, drawing trees. They'd say, okay, well, there you go. And that's our random distribution. Or they might even say, well, it's a bit too cluttered up this end. But in fact, that isn't a very good random distribution. In fact, what would happen in reality is that certainly trees would grow to boundary conditions, but also you'd get clusters and clumps. And this is just what happens in nature, and it's really to do with how stuff happens in the real world. You might get a whole patch of nothing over here, and then you might get a whole clustering for no apparent reason over here. In much the same way, if I asked you to throw a coin, most people would assume that it'd be, heads or tails. And if you asked them to list them down, maybe heads, tails, maybe tails, heads, heads, tails, heads. But what you wouldn't expect people to list is what would actually happen occasionally, which is just a bunch of tails and then a heads and then a tails and then a bunch of tails and heads. Because most people say, well, that coin's biased because it's got, a bunch of tails in it. In the same way, the distribution through here tends to have clusters and clumps, and that's how the real world operates. And, this is, again, to a certain extent, counterintuitive, but that's just how it actually is. And so we have these concepts of noise and we think of noise as being truly random. I actually have here in Flame the ability to generate noise, right? So I can ask to create colored noise. And so here's a frame of colored noise. And that is what most people think of as being completely noisy. And that is true, it's noise. If I zoom down on this, it is in fact colored noise. And if I get down to a significant enough level, you'll see that there is a little bit of clustering going on here. But the concept of noise is this, or a black and white version. Let me give you a black and white noise. Okay, and so this is our kind of classic white noise. We don't see a pattern here. It just seems equally and evenly distributed. But what tends to happen most in computer graphics is, in fact, turbulence, or this kind of an effect. This is a sky, and it's exhibiting all the properties of turbulence, in other words, noise in nature. Because you'll see here, this is a big dark patch, these are big white patches. We can see patterns in this. In fact, most people see horses and fluffy bears and stuff in clouds. And that's just what tends to happen. And turbulence is what we see in nature. And turbulence and this kind of pattern of noise, for want of a better term, is what we're up for. This is, in fact, the thing that we need to deal with the most. What we're looking at when we look at this picture here or this picture here is stochastic noise, and that's a really important concept to understand in computer graphics.
So stochastic process is one whose behavior is non-deterministic. In other words, it's like a system who, if I'm here, the next place I'm going to, the next state, as we call it, that I'm going to, is determined by the process, but also by some random element. And so we need to deal with that random element. So how does this appear in effects? How do I actually sort of deal with these concepts of octaves and turbulence and stuff when it comes to computer graphics? Well, quite literally, you're likely to see exactly those terms. If I was to go now to the persistence of vision piece of code, this is a 3D free software. It's available in Linux and OS X and Windows. Let's have a look now on the flame at what I would actually see if I was trying to, for example, add fog to a scene because I wanted to add some kind of depth cueing into a classic visual effects shot.
All right, so if, let's say we wanted to go in, as I said, to persistence of visions renderer and have a look at that. This is what we'd see if we looked up fog. Okay, so this is the sort of definition of fog as to how it runs inside that particular program for producing depth cueing and stuff. And you'll see here that the fog items, fog type, and it has two types, and then it has the distance, and this is the distance between where we are and where we want to be in the picture. So the camera to the object, as it were. The color, of course. Then there's turbulence. I'm going to come back to this, and turbulence depth, and some other stuff there. That line there, what's that? We'll come back to that. And then there's offsets, because if we were doing fog type 2, which is ground fog, we'd have some offsets for how much it is starting off the ground. Normally it starts a bit off the ground, and then also it doesn't go right up to very high. It's sort of, you might have fog that's, starts a foot off the ground and stops about 3 or 4 feet off the ground. And then there's a couple of other things, some transformations and stuff. So that's what's going on. So what are these turbulence functions, and what are these other octaves and other qualifiers that we're seeing in this definition in persistence of vision of fog? Well, to do that, we need to think about how we might actually mathematically represent this turbulence. And one way that to think of this, I guess, is to think of it as if, imagine you drew kind of big blobby objects. So imagine I was drawing in 3 dimensions, and I was drawing you a bunch of weird blobby shapes. And those weird blobby shapes all had volume, right? They're all like 3-dimensional. And so they exist as kind of like what I might call metaballs, or you might call globules, or big hunks of whatever sitting in 3 space. Now imagine for a second that I could somehow get a magic razor and do a cut that would actually cut through these, and it would slice off anything that was above the line, as it were, of our image plane. A bit like if I flooded a valley with water, and this is the water now, and the water obviously lies evenly, and above it sticks out the rocks. So that's a model. If you could have that model in your head of how that is existing. I'm now going to show you this image here. Now this is noise. And those are the kind of the blobs I'm telling about. And this is a slice through that noise. Now the thing about this noise, and this is coming now from Mental Images and from our good friend Zap, is I can animate that, and I can change the settings on that noise. And that's what some of those qualifiers were we were looking at. But if you sort of think about what's going on here, you can think of those rocks or those blobs as going up or down, and the water sort of creeping around them and flooding some valleys and other hills poking through. But you get a sense that we're at the same actual height above the table. In other words, to go back to my picture here, if I was to imagine that we were just looking at that plane, then my camera is, up in the air here somewhere. And that camera that's up in the air that's looking down on the plane is staying at a kind of the same height off the plane. Yes, we're changing the blobs, and yes, the water is moving in between different valleys and stuff, but nevertheless, my actual eye is sort of sitting at the same sort of helicopter level above the valleys as it was before. Animating the noise is changing that, and we've got some of these properties that we're seeing now in terms of the clustering, but we're not actually changing anything in terms of like what I'm going to call the octaves of the noise. Now I'm going to show you turbulence noise again from Mental Images, and I'm going to show you this at different octaves. So whereas before we were basically looking at animating the valleys by moving the blobs around, as we change the octaves, we are changing, in a sense, the way at which we're looking, and almost like the clarity upon which we're looking at the different turbulence noise. So I'm not actually now animating the noise so much as I'm changing the octaves. So you can see here at this level, it's very smooth transitions between the black and the white, and I kind of get a more detailed kind of breakup of those as I go on. I'm not actually changing blobs to blobs, but I'm actually getting like a closer detail. I'm sort of seeing different patterns happening. And so one of the two things you want to need to do with noise is you need to change the fundamental underlying noise itself, the noise that's being generated. You might want to animate that, but you also have to consider the octaves, which in a sense is the pattern that's going on. And if that idea of there being kind of more and more detail the harder you look sounds familiar, it is, because actually it's the concept of fractals. This is fractal noise, again from our friend Zap at Mental Images, and you can see here that as I increase the fractal amount up and down in its terms of its octaves, you see how we're sort of almost like bringing it into focus. Now, fractals are self-referencing at different scales. In other words, if you zoomed in on this, you would see the same sort of pattern reoccurring at different resolutions. So if I was to take this section here and do some kind of massive zoom on it, I'd sort of get to something similar to where I'd been. Now, of course, I'm just doing a zoom in post as opposed to doing it properly, but that's the principle. And we're going to come back and look at fractals, this idea that that we have something in nature that automatically does this and does it at different resolutions. So to stay with turbulence for a second, that function that we were looking at for the fog is basically looking at not only how the noise is set up and how we might animate it to give us these kind of patterns, but also the octaves upon which we're looking at it. And octaves are a really important concept. And of course, it relates back to episode 1 when we were thinking about that whole concept of banging hammers together and having these naturally occurring subdivisions. If you remember the hammers that Pythagoras had, if he banged them together and they were on his rocks, he banged away at this rock with a hammer that was exactly half the size of a hammer above, and he would get really interesting sounds that were sort of harmonious. And then they called these natural subdivisions in music octaves. And so that idea of sort of naturally occurring smaller sub-areas has been around for many a day. So the last thing to mention is the idea of noise itself, which is that a computer is inherently really bad at generating noise. When a computer is asked to make this noise, it doesn't actually have the ability to very easily produce anything that's particularly random. It's just hopeless at it, in fact. Now, the reason that it's hopeless at it is because, as you can see here, when I ask it to generate 2 frames of noise, they're actually the exact same frame. It's generated exactly the same thing twice. And you might say, well, how is that possible? What's the probability that it would generate noise that looked exactly the same? Well, of course, it isn't actual noise. In a computer, when it tries to generate noise, it just simply produces a pattern that we think of as noise, normally based off a seed. And if, in this case, I've just generated 2 frames one after another, the seed, all the conditions are the same, so it produces the same, quote, random pattern. But of course, it isn't random. Computers are really crappy at doing random. To get around this, designers do all sorts of things. They might look at the seconds in terms of the time that the computer's clock is set to and use that as a random number, even though it isn't, of course, it's just a number, but at least it's a number that's unlikely to be the same every time you press the button to generate the pattern. Now, in one sense, that's hopeless, but in another sense, it's exactly what we want, because if we were trying to artificially, in, say, Mental Images, generate these clouds, then we'd need to generate them the same every time we did the render. And if every time we did the render we got a different noise pattern out, which fed into a different turbulence pattern, we'd get different clouds every time, and we don't want that. We want to have controlled noise. So the noise in the computer that you're working with is not actually real noise, but nor do you actually want it to be. You want it to be repeatable noise so that the render changes only when you want it to and not every time you hit the render button, or even, for that matter, every time you preview a shot. Okay, the actual definition of what's going on with the fog is that the pixel color is related to the object color and the fog color, and as one goes up, one goes down, which is why one's 1 minus and one is 1 and 1 minus, sorry. And then it's related to the distance that the fog is and the distance we are into the fog. And so it's just a really simple concept. I don't want to go into the maths of that. What I go into is a discussion of how the fog is generated.
So in this example, there are two fog types. There's type 1, which is like a constant fog, and then they have another one in this particular program, which is ground fog, which might be lifted off the ground a bit. And the constant density everywhere, 1 versus the density that sort of starts a bit off the ground and then thins out as it goes above a certain point. So there are going to be offsets for that. That makes perfect sense. I would expect that. What else is the fog thing asked for? Well, it asks for a few other characteristic things, the distance from the viewer, that kind of stuff. And it makes sense, right? The idea of fog is that you're going to have a colour of an object and it's going to be affected by the fog. And of course, the further back in the scene the object goes, so the fog is going to influence things more. That makes sense. The colour of the pixel, the intersection depth, and there's formulas for that to calculate it. Now, I don't want to go into those right now, but you'll see that in the middle of all of this, there are actually some keywords. There's obviously pivotal things that you work out to make sure that you get the mix right, so that 64% of the colour of the object is its original colour and the other 36% is the fog. But when it comes to determining the fog, the density of the fog, it discusses, you bet, turbulence. Okay, and the reason it asks for turbulence, and then in particular octaves, is what we saw before. Now there are a couple of other aspects here. There's a thing called omega, and there's another one, a couple of other modifiers in there. But basically that's exactly what it's doing. It's asking you explicitly for the turbulence and the octave level that you want, because it will affect how the fog looks and it'll affect the scale upon which things are going on. Now, interestingly, as we saw before, you could be dialing in, if you were over in mental images, not just a different type of fog based on turbulence, but in mental images you could be doing a fractal fog. And the reason I wanted to touch on this now is because this will become important later when we do fractals, is that it's the same idea as octaves in a sense. Octaves gives us, as we saw, fog at different kind of like scales, like how close I'm standing to it and how far away I am in terms of whether it gets sort of that fine detail or not. And that octave sense is not dissimilar to the idea of fractals and how they have self-replicating or self-referencing geometry at different scales. So pi, golden ratios, incredibly useful, but the thing you're probably going to touch more and need to understand more, honestly, in CG, is accurate noise, and more importantly, an understanding that what we really want more than anything else is for things to behave not in a completely random fashion as our perception of random would be, not as I showed you with the trees where you think you've distributed them randomly and in fact you very conveniently had all of them separate from every other tree and relatively evenly spaced. And part of that is just simply our inability to deal with probability. It's our inability to deal with making sense of probability. It doesn't come intuitively to us, and yet it's the turbulence, the kind of connected nature of randomness that actually gives realism to what we do. And it's that I said we'll pick up on, or that we will pick up on more when we come to fractals. Well, that's it for this week. Thank you so much for watching. I hope that's made some sense. We're going to go into some more hardcore maths again next week. I wanted to give you a slightly different perspective this week. And as I say, we are moving between some huge branches of mathematics each week. So I'm trying to give you an overview at 10,000 feet and maybe pick out a couple of interesting aspects so that it becomes less daunting to you. And I hope that's working for you. Please let me know. Give me feedback in the forums. Until next time, I'm Mike Seymour. See you.